Hello, Ong. So I am looking at your project 5, and also see your project buck boost converter. Thanks for sending that over. This video will review your thoughts, questions. For your question on Stackup, immediately I would say the Stackup with the dielectric prepreg. I see the core with their thicknesses. The thickness is pretty thick, 10 mils is pretty thick. If you can get it down to 3 mils, that would be good, but not mandatory for a power board. For your dielectric in between, I see your thickness is 5 mils. Okay. This is this is decent. This is decent. Okay. So this here, why? Because when you have your power and ground plane, the closer they are for together, the more capacitance they have. And the more capacitance there is, the more current can be surged through to from the more current can be sourced from ground or sunk to ground, excuse me, and sourced from power through to ground. All right. So plane to plane capacitance is very nice here. Also current, you're getting more capacitors for your quick current draw. This will reduce the chances or likelihood of dealing with rail collapse or ground bounce. Okay. And also, the wider your planes are, or once you actually have proper planes, which I'm sure you do, then the lower the impedance, then the less likelihood of getting, you have less noise and also less signal. I don't know. I'm trying to remember you have a lower impedance, so you're gonna have fewer issues. All right, signal integrity wise. In this stack up, two cores are unlike normal stack up. Okay, so we have for this one, with this core, the core is too far away, 18 mils. I mean, you're gonna get lower capacitance between your ground plane and your power plane if you do it this way. This is actually for, I would say, current sync purposes, not the best. You'd want your core closer to each other, but let's say that's the closest you can get them, right? The next thing is for EMI. So for EMI purposes, does EMI even matter in this power electronics as a buck boost battery converter? Of course it does, but mostly around the inductor loop not being close to critical parts like I don't know if you have your control chip, for instance. Um, if it's sensitive to, like if it doesn't have internal shielding from electromagnetic interference or fields. Okay, the next thing we have is what else? Foil, prepreg, solder mask, foil, signal, copper, core. Yeah, the thicknesses between the foil slash copper, the foil to copper, at the top layer and the second layer, very nice, that they're so close. Very nice that they're so close. So that's good. I would take advantage of that in a stack up by having the voltage on the top. Okay, like having signal voltage and then the second layer being ground and then the third layer being ground and the fourth layer being signal voltage. Now you have this case where your your reference voltage at the top layer can be one or two sets of voltages that have the same ground reference plane, while your other voltage, let's say 12 volts, whatever, on the bottom here, can immediately reference your second ground reference plane. And then they don't have to go in between, they don't have to pull their voltage reference from a ground that's, signal 4 or voltage 4 doesn't need to pull its ground reference from layer 2. Okay. And where there's lower capacitance, okay, where you want higher capacitive coupling between voltage and ground, between 3 and 4 and 2 and 1. So I put ground in layer 2 and ground in layer 3. See if you could figure out a way to reduce the traces on the board. If not, it's not the end of the world. It's just kind of the worst for EMI, if that even matters. The inductor that you'd have on the top or the bottom of the PCB, probably on the top, you'd want you'd want its fields to be captured as quickly as possible. So I would put it on the ground or even have ground around here, shielding it in a way. For the stack up from zero circuits, well, as add more internal power planes like an I. No, not necessary to add more in the internal power plane in high-speed boards. Why? Because unless you have, let me see, unless you have high-speed signals and EMI that you're concerned about, then don't worry about well, for your inductor, it's going to be outside on or on the bottom. I mean, the top or the bottom, so outside the PCB, the outer layers of the PCB. With some via stitching, good grounding around the inductor, and a ground power plane below the inductor, and keeping components far away from the inductor, far enough away from the inductor, if it's an external one as opposed to internal, then you should be okay. I won't say you'll pass an EMC compliance test necessarily, but depends. It really depends on how you design it and do your calculations and simulations on the PCB. For the Stackup from CR circuits, is that plain capacitance? It's a little thick, I must say. If you can get it lower, that'd be great. But if it can't get lower, it's not the end of the world. For VN and VBAT, are they just enough with top planes? Good question. Well, to find that out, you need to know what thickness of trace is going to accommodate the current, the maximum current that VN and VBAT can need to accommodate. To find that out, you need to calculate the maximum current draw that every component on the PCB in this design will be pulling, every chip, every component. Then sum those together, multiply that by 1.5, okay? Once you do that, that gives you your VN, current, maximum current, or peak current. And you also want your continuous current, right? But that's generally that. It's continuous current multiplied by 1.5. That 1.5, that'll be a peak current. Then you go to a trace width calculator, IPC 252. Let me see. Trace width calculator is one of those. The updated one. Go on CR Circuit's website, do the trace width calculation. If your traces hit that minimum trace width calculation, you can then widen the traces to accommodate more current. Okay, so as long as you hit that minimum trace width, let's say 30 mils, 20 mils, whatever, you're golden, and then go beyond that for that particular thickness. Let's see, dielectric thicknesses are different from normal. I can't decide which one is better. Better depends on, it depends on, normal and better depends on your application. For high-speed digital designs, definitely the thickness matters. For power electronics like this one, the thickness also matters for capacitive coupling. But, and for high-speed things, you'd want to be concerned about dielectric constant and dissipation factor. The thickness does matter for, let me see what else. I mean, thickness affects impedance, trace impedance. So if you have single trace, single-ended impedance for traces, right? And you have differential impedance, that makes a difference. I mean, the thickness makes a difference for those, but as long as you're hitting those impedances with the appropriate trace widths, I think you'll be fine. Granted, the thicker your PCB, the further away you have them, your traces from your plane, the higher your impedance is going to be per trace. Okay. The skinnier you make that means you'll have to make your traces wider, and it's going to take up more space the further your traces are away from your ground plane. All right. So that answers that question. But for the most part, I mean, you're going to be fine with this power electronic board. You'll be all right. Unless you have some like USB 2.0 that requires a specific differential impedance, and the traces get too wide, like 16 mils or 20 mils for your differential traces, and then you don't have space because your planes are too far away. Then, because your layers are too far away because of the thickness of the dielectric, then there's some concern. You might want to thin that out, talk to your manufacturer and see what they can do. Okay, so that's my summary based on your questions. Hope this helps, and I'll see you in the next video.